This video is going to be a review for some of you guys and brand new for some of you guys. What we're going to do today is a little bit unusual in terms of a starting point for cell metabolism, but what I've found is that one of the hardest parts of everything with biochemistry is how do I put the pieces together? No one concept, no one reaction, no one enzyme is difficult, but how do they fit together tends to be the difficulty. There's certain questions that I hear over and over from you guys that give me the idea or tell me that you're not putting the pieces together. So what I've started doing is introducing the metabolism with this discussion. Then I always try to wrap up quarter two with it. I go back to it with quarter five if you want me to. And I notice those questions that give me the idea that you're kind of disjointed in what concept fits in where. Now that we have this video, I'll be able to just give it to quarter five to put the pieces together if you need it. So anyway, for quarter one, you guys are going to hear some words that you don't know what they mean yet, and that's fine. What we're going to do is we're going to talk about what processes we're going to do, and it's a little bit of a coming attractions type of thing. So just go with it, with the words, and what we'll do is we'll use this diagram then as we progress through cell metabolism, and we'll be able to say, we went from here to here yesterday. Today we're going from here to here, tomorrow to here, kind of thing. And you'll see the progression. Quarter two, quarter five, this is what I redraw every time when I'm saying, here's what we're doing. Here's how it fits in with everything else. So we eat carbs, we eat fats, and we eat proteins in varying quantities and qualities. And the qualities part, I'll leave to Dr. Krabbe. He does that with the nutrition class. So we start the discussion with carbohydrates at a very traditional place, and we start it very traditionally with glucose. Glucose is the carbohydrate that you eat the most of. First process we do is glycolysis. We take that molecule of glucose to pyruvate. We use our discussion of glycolysis as kind of a laying the groundwork for how we're going to approach metabolism spot. So, like we've done all along, one of the best skills you can develop as a student is predicting questions. Look at a topic, think about a topic, and think, what does it make sense I would get asked about this? Because when you look at it and think about it and decide, here's what it would make sense that I would get asked about this, you are probably going to be right. And it directs your studying very, very nicely. So anyway, we start that thought here in terms of applying it to metabolic processes. And we go through the steps from glucose to pyruvate. And we say, well, what would it make sense you get asked? Well, of course, the reactions. What molecule makes what molecule makes what molecule? The regulatory enzymes. What enzymes regulate this process? As in turn the process on and turn it off. What molecules give them the signal to turn it on and off. So we're going to see that as a continuous theme through everything that we do. So one of the things the regulation comes to is what's the point of the process? So every single process we have to know what is the point. So the point of glycolysis is to start processing my carbohydrates with the end goal of making energy in mind. So glycolysis is an energy making process. So that cuts down the amount of stuff you need to know about regulation right there. Some of you guys who have taken biochem before I'll hear you saying, well, this molecule regulates, and the regulator is whatever. And I'll say, so when do you turn this on or off? You'll say, well, when I have this molecule or don't have it. I'll say, yeah, and what's that mean? And you give me the deer in the headlights. And what I'm trying to get from you is, if this is an energy making process, I turn it on when I need energy. I shut it off when I already have energy. There's half of regulation done for you right there. Then all you need to know is remember where my regulatory points are, what exact enzymes, what molecule gives me the signal that I have energy or I have the need for energy. So that simplifies it right there. That little bit of understanding cuts the volume of memorization down. So you have to know regulatory enzymes, what regulates them. Here and there'll be another enzyme that you have to know for a particular reason, and we'll talk about that. Glycolysis has one of those. That was our phosphoglycerate kinase for you guys who are watching this as a review. So you also are going to get asked how many ATP kind of questions. And we use the analogy of money with ATP. It's a big budgeting project. I'm making ATP all the time. I'm breaking ATP all the time. So I've got to make sure that I'm making more than I'm breaking. Like when you're looking at the budget for your office, you're going to be spending money in your office. You've just got to make sure that you're making more than you're spending. So when we look at how many ATP questions, there's 3 pieces of information that we need. So the first piece of information that we need for a how many ATP question is per what. So this is the one where I say, let's pretend I'm your accountant, and I say, how much money did you make? We're talking about your office. How much money did you make? You're going to say, well, what? Per last month, per year, per what? Same thing with ATP. Per what? Glycolysis, glycolysis splits the glucose. We have a split here. So per what with ATP refers back to glycolysis. Per molecule before or after that split. That makes a factor of 2 difference in your answer. So that concept kind of belongs to glycolysis, even if I'm asking you how many ATP per something 2 processes away. Really easy to forget that when you get 2 processes away. So I always chase you back on that. Another thing you have to know in a how many ATP question is how many ATP did I make versus my net or my yield. The analogy with money is my gross versus my profit. How much money did you bring into your office last month? Just how much money came through the door, not counting what it cost you. That's my gross, or that's how many ATP I made, versus my net or my yield in ATP, or my profit in money. How much money was left after you paid your light bill, your salaries, your whatever. How many ATP were left after I counted the ATP it cost me to get those. That concept, we've noticed, for those of you who are reviewing with this, that belonged to glycolysis. Per glucose I made 4, I had a net or a yield. Those are the 2 words you're going to watch for. My net or my yield was 2 per glucose. Then the next thing that you have to know when you're answering a how many ATP question is, do you mean how many ATP, real ATP, versus how many ATP equivalents? The hardest part of this is no one's going to say real ATP. They're going to say how many ATP, just that's it, not real ones, or how many ATP equivalents. That concept belonged to the Krebs cycle, the process that didn't make me any ATP, but made me a whole bunch of equivalents. So that's like, how much money did you bring in spendable cash, that's your real money, versus how much money did you bring in the form of insurance slips that you have to submit, credit card stuff that you don't have the money for yet, checks somebody wrote, whatever. That money came in. It's money that you will have, but you don't have it yet. That's an ATP equivalent. I made that ATP equivalent. It will be worth whatever number of ATPs, but I don't have that yet. I've got to go to the bank, cash those equivalents, and I'll get the ATPs from them. So what you noticed, for you guys who it's a review, that was the Krebs cycle concept. And especially everybody loved to ask you the how many ATP question with the Krebs cycle, meaning real ones, but of course we never say it. We just say how many ATP. The answer is 0, but giving you all kinds of stuff to multiply 0 by just to mess with your head on that one. So, how many ATP questions? You know you're going to see those everywhere. So the other thing you have to know with each process is, where does it happen? Where does it happen on the cellular level, and where does it happen on the tissue level? On the cellular level, we have our most of the time rule. Most of the time I do energy making processes in the mitochondria. Most of the time the cytoplasm is about storage. The reason the most of the time rule is the most of the time rule and not the all of the time rule is glycolysis. Glycolysis is an energy making process that happens in the cytoplasm. So we need one of those. It's an energy making process, but it happens in the cytoplasm because there are parts of you that don't have mitochondria, and all of your parts need energy. So we need something that works for parts that don't have mitochondria. The example you see of that most frequently is that of red blood cells. So red blood cells use glycolysis, kind of an inefficient little energy making process, to make their energy. So anyway, glycolysis we did in the cytoplasm. Then we did the pyruvate dehydrogenase complex. That was our ticket to get our carbohydrates into the mitochondria. So this also gave us the chance to lay some groundwork on how questions get asked, because you noticed things with this, like I have two approaches to questions. One is very application-y. What am I doing? I'm getting into the mitochondria with my carbohydrates so I can go and make energy, get the energy out of those molecules so I have energy for my cells. Then we started to see this nitty-gritty kind of question approach, which is the way something like this, a topic like this, goes into multiple choice questions. So, Luke, stop. So, sorry about that. So, we saw things like all of the following are products except. Lukey, come here, stop. All of the following are products except. All of the following are reactants except. And then that way, that look to see if you knew what goes in, what goes out. It's a really common thing to get asked. So we got to our acetyl-CoA, went through our steps, went through our story. We're in the mitochondria. Now we do the Krebs cycle. So we do the Krebs cycle, also known as the tricarboxylic acid cycle. Also known as the citric acid cycle. When I give you multiple names for something, I do it for one reason. I think there's roughly equal odds of you seeing a question with any one of those three names. I'm not giving them to you to give you more stuff to know. You guys have enough stuff you have to know. So I think it's equal probability of seeing any one of those three names. So the Krebs cycle had a description like all metabolic roads meet here, things like that. So at the point at which we're in the Krebs cycle, we're processing not only carbs, you remember the carbs because that's how we got there, not only carbs, but also fats, also proteins. So one of the aha moments that helped put the pieces together with this class is this. Any one of these processes, even though we learned it, step 1, step 2, step 3, and so on, even numbered it in the PowerPoints, even though I discouraged you from numbering. It's the only way I could figure out to keep the PowerPoint straight. We learned it in that very linear, stepwise manner. And academically, I don't know any other way of doing that and being complete. But the big aha moment is I might jump in the middle of the Krebs cycle. I might jump out in the middle of the Krebs cycle, get that molecule from somewhere else, go somewhere else with it. So our fats and our proteins also jump into the Krebs cycle. So that's an important thing to remember. And I love asking you guys the question, which of the following molecule is processed by the Krebs cycle? A, carbs. I throw the bait right out there. B, fats. C, proteins. D, all of the above. You're going to pick D, all of the above. Because even though we only have done carbs when we started, it's definitely in all of the above. So we did the Krebs cycle then, or we will do the Krebs cycle, depending on which class you're in watching this. And the point of the Krebs cycle is to get me the energy out of whatever molecule I'm feeding in. So acetyl-CoA comes in containing a lot of energy. So I go through these stepwise reactions. And what's kind of hard about it is there's a big point you can miss. So I go through these steps, these reactions, and I come back to a molecule, oxaloacetate, that is both a product and a reactant. Well, what did I accomplish if I come back to a molecule that's a product and a reactant, closes the loop, and starts the cycle over again? That sounds like a whole lot of nothing. Well, oxaloacetate is what I made in the last round of the Krebs cycle. It reacts with acetyl-CoA to kick my Krebs cycle off. So it does cycle through, and it's actually not the same carbons you end up getting back. But here's the thing. Acetyl-CoA is a very high energy molecule. Oxaloacetate doesn't contain much energy at all. We get focused on what makes what as we go through and kind of lose the forest for the trees a little bit when we focus on that. But we make other stuff. We make stuff that actually leaves this cycle. And what these are, you guys who are reviewing know these molecules as soon as I write them down. These are electron carriers loaded up with electrons. These are ATP equivalents. These are checks you're writing to yourself for ATP. Here's the energy leaving. And we do the big counting and accounting project where we talk about how many ATP will this be worth, how many ATP will that be worth. So at the moment at which you have these molecules with the electrons on them, that's where the energy is from that glucose that you ate in the first place. So you ate that glucose, lost a little bit of energy through glycolysis, a little bit through the pyruvate dehydrogenase complex, still had a whole bunch left when you got to acetyl-CoA. Oxaloacetate reacted with acetyl-CoA, kicked off my Krebs cycle. I went through all my steps and got oxaloacetate back. Acetyl-CoA had lots of energy. Here's where the energy went. So that by the time I get back to oxaloacetate, I don't have a whole lot of energy left. So here's where it went. I wrote myself a check, or several checks, for ATP. My checks are in the form of NADH and FADH2. So the purpose of my Krebs cycle was I got my energy out of my acetyl-CoA. Here's the form I got it out in. So that's all great. I have checks for ATP. that's you sitting in your office, sitting at your desk with a bunch of checks and a bunch of bills to pay, we'll say. So great, I have checks. I can't pay my bills with somebody else's check. I need to cash those checks. So we cash the checks in a process known as the electron transport chain. The electron transport chain is a really cool process. And it's the bank. I'm going to feed the NADH in, feed the FADH2 in, and I'm going to convert that energy into energy that allows me to reform that high energy phosphate bond that attached that third phosphate onto ADP, turning it into ATP. And when we tell this story, we tell it with the analogy of a battery. We have a couple of cells that happen to be in the mitochondria. We build up this gradient, then use that gradient to replace the energy for that high energy phosphate bond. So we do it very conceptually. Then we go back and we name what molecule does what, who moves what, to build up and dissipate that gradient. But anyway, our electron transport chain, that's our bank. That's where we cash our checks and we ultimately get our ATP. So we told the story initially, and we will tell the story for you guys who are seeing this for the first time, that we're going to build up our story, build up our metabolism picture in kind of a unique way, I guess. It's like we're going to build, let's say we decided we're going to build I-95. So we're going to build a highway. I-95 goes down the east coast of the U.S. from Holton, Maine to Miami. So we're going to build this. So we decided the most efficient way to build this highway is we're not going to worry about on-ramps and off-ramps yet. We're just going to build the highway. Then on-ramps and off-ramps get easy. So that's the approach that we use with metabolism. We're going to go from glucose, oops, it's an awful square, to ATP. That's Holton, Maine to Miami. And we have our highway now. Now we can go back and add on-ramps and off-ramps. And like we said, every process, even though we very linearly say, here's step 1, here's step 2, here's step 3, we can jump in at step 3 and go and do something else, go 1, 2, 3 and go somewhere else. Or we can skip 1 and 2, bring the molecule that you make at step 3 in from somewhere else and continue. So those are our on-ramps and our off-ramps. So that was our highway. We had some other kind of asides though before we did too much with our highway. One of the things that we didn't talk about yet is oxygen. We breathe in oxygen, we breathe in air because we need the oxygen in the air. And one of the places we need that is right here in our metabolism. So for pyruvate to continue into the pyruvate dehydrogenase complex, I need to have sufficient oxygen. So for the sake of space, I'm going to write have O2. And what I mean by that is I need sufficient oxygen. If I don't have sufficient oxygen, my pyruvate is going to do a little bit different process. It's going to go to lactate and go through a process called the Cori cycle. And I'm saying no oxygen, and what I mean really is insufficient oxygen. And again, I'm putting no for the sake of space. If you have no oxygen, you have bigger problems than all of this, obviously. So what the Cori cycle is a process where I do kind of a do-over loop if I'm not getting enough oxygen in. The most common place you're going to see the Cori cycle story told is that of an exercising muscle. So it'd be something like I'm out for my morning jog, and of course my respiration rate increases as I'm running because I'm trying to bring enough oxygen in to give the muscles the oxygen they need to do all this, make me ATP and keep me running. But I'm huffing and puffing, I'm not getting enough oxygen in. So I still go from glucose to pyruvate. Pyruvate then looks around. Do I have enough oxygen? The answer is yes, I continue and make ATP. The answer is no, I go to lactate. I go to lactate in that muscle, send the lactate to the liver converts it back to glucose, sends it back to the muscle, and I try again. So, get to pyruvate, hope I have enough oxygen. If not, keep going and going and going, looping through. So we'll talk about that, but that's kind of my do-over loop that I do if I don't have enough oxygen. I need oxygen to finish the process of getting my ATP. So another part of the story that we'll have. Another story we're going to have is I have a way of making glucose if I need it. So if I don't have enough glucose, I can make it. And I can make it out of a few different things. I can make it out of fats, I can make it out of proteins, or I can make it out of pyruvate. So we're also going to have gluconeogenesis. Break the word down. And I don't mean to necessarily have it just under fats, and it's really not. It's a way of making glucose. Break the word down. You should have gotten that right from the start, you guys that are new at this. And break all of your words down. Gluco is glucose, neo, new, genesis, generating. So I'm going to have all kinds of words ending with genesis, generating, or lysis, breaking. So be very cognizant of that too, especially since words starting with GL are going to start blending together. Quarter one, I'll say this 100 more times to you. Quarter two and quarter five, it's a reminder, and you can tell quarter one why to do it. We're going to have so many words starting with G. Next letter will be L. Next letter after that will be a U or a Y. They're going to blend together. When you're in a hurry taking notes, you want to abbreviate. Don't. It'll haunt you. You'll be sitting there staring at it. What's G6P? What's G3? Whatever. Because there's so many G words. Abbreviating phosphate with a P is fine. It's the only P we have. If you want to abbreviate fructose with an F, do that too. It's the only F we have. So G words, though, be careful. So anyway, we'll have done all that, and then we'll go back and we'll say there was a big underlying assumption in this story. The assumption is I'm eating glucose as I need it for ATP. Well, do we do that? No, we don't. We eat, we stop, we eat, we stop. But our need for ATP does not stop. Also, when do I need the most ATP? I need the most ATP when I'm working out. Well, I'm not eating when I'm working out, so I need some kind of leveling out system. I don't eat constantly. Well, some of you guys do, but even those of you guys who seem like you do, it's not at the right rate. When you work out, you need more. You're not eating when you're sleeping, stuff like that. So I have this molecule that's called glycogen. Glycogen is kind of, sort of, a whole bunch of glucoses hooked together. So when I say kind of, sort of, what I mean is I want this idea in your head, and we'll come back and talk about what the kind of, sort of means later, what kind of bond, things like that. But the reason I say it's kind of, sort of, a whole bunch of glucoses hooked together is this. When I have extra glucose, what's a good place to put it? In this molecule. Save my extra glucose for later. Make glycogen. And that's what I do. That's how I get from breakfast to lunch, lunch to dinner, whatever. Then, let's say it's 11 o'clock in the morning, my blood glucose levels are dropping, I'm fading, I need some glucose, it's not lunchtime yet, I'm not eating, what's a good place to go looking for it? Go and break down my glycogen. So my glycogen is my short-term storage. That's my breakfast to lunch, lunch to dinner, whatever molecule. I also store it in the muscle for an extra boost for the muscle when the muscle is doing something. So that's my leveling out molecule. That's what gets my time frame working. But we still have another big underlying assumption in that. That assumption is that I'm eating what I need over the time period that I need it. So this is my short-term storage. So what I'm saying basically is that over the course of a day or whatever time frame we're talking about, I'm eating the right amount. I'm just not eating it at the right time. So I'm eating, say, 2,000 calories a day, and I'm burning 2,000. This is like my leveling out molecule, my little reservoir to balance out the time part of it. But what if I don't eat exactly what I need every day? So let's say I'm laying on the couch every night, binging Netflix and eating Oreos. So I'm taking in 6,000 calories a day, but I'm only burning 2,000. So what I'm going to do then is I'm going to make fats. So here's what I'll do. First part of my energy that I bring in will go to ATP. Then I'll take the next part, I'll make glycogen. Glycogen is a finite thing. I have a certain capacity. When I fill it up, it's full. So then next part of my Oreos will go to glycogen. But I'm still laying on the couch and I'm still eating. I'm going to fire up glycolysis again in the liver. I'm going to fire up the pyruvate dehydrogenase complex in the liver. My Krebs cycle is going to look around and say, you have more energy than you know what to do with. That ship has sailed. I'm not firing up. So I get to acetyl-CoA and I stop. So we say things like acetyl-CoA equals energy. I got to acetyl-CoA, made my acetyl-CoA with the end goal of making energy in mind, but I have enzymes in the Krebs cycle that are regulated by energy. If I have energy, they stay shut off. So my Krebs cycle doesn't go. My acetyl-CoA leaves the Krebs cycle and goes and makes me fatty acids. So I go and make fats. I make fats and I get fat as I eat my other 5 boxes of Oreos or whatever. So fatty acids are kind of sort of a whole bunch of acetyl-CoA hooked together. The kind of sort of means the carbons in the fatty acid are the carbons from the acetyl-CoA. But I say it that way because I want you to have the idea where it's coming from and that it's a whole bunch of energy. Because acetyl-CoA, we said, equals energy. If I have a whole bunch of acetyl-CoA making up that fatty acid, that should sound like a whole bunch of energy. That's what I want it to sound like. Right at the beginning, we asked the question, before you had done any biochem, at least with me, what has more calories, a fat or a carb? And you guys very intuitively, from everyday knowledge, said, well, a fat, of course. And in general, that's true. That's because it's all the acetyl-CoA made into that fatty acid. So those are steps we go through and talk about. Quarter 2 and 5, we did it. Quarter 1, that's where you're going. So this is my long-term storage. When I make my fatty acids, I need to transport them. I'll turn them into a triglyceride or a triacylglycerol. I'll put that in the bloodstream. I'll send that off to the peripheral tissues, store it wherever I need it. So let's think about something. Let's think about an application here. Let's say I've been laying on the couch, eating Oreos, binging Netflix, and I go to the MD. Well, actually, you guys can do it, depending on what state you're in. I go and get my blood drawn. I get a metabolic panel done, and the doctor says, ooh, your triglycerides are through the roof. My triglycerides are through the roof. what are you seeing in that blood? You're seeing that molecule that's the transport mechanism for all these fats I'm making from all these Oreos I'm eating. You're seeing that molecule taking that extra energy molecule off to storage, off to long-term storage, saving it for later. When you guys do labs, think of it that way. What is that molecule? Where did it come from? It's another place where you can memorize and make your life really difficult, or you can understand and make your life easier. So, where did that molecule come from? Those triglycerides. We've either done the steps, or we will go back through that rather than memorizing. If it's too high, it means this, too low, it means that. So anyway, that's my fats, my fatty acids. So how did I get there? I got there from a sustained caloric surplus. Now let's turn that story around. Let's look for a minute at glycogen and fatty acids, what they are. And again, we'll use money as an analogy. So I told the story that I'm eating, a case of Oreos a night or whatever. I have way more energy than I need right now. So let's look at it instead. You're in your office now. It's 10 years from now, and you just got paid. So you set it up. You pay yourself once a month, we'll say. So you just took that check from the office, your salary, and what are you going to do? Well, the first thing you're going to do is you're going to pay your bills. You're going to pay, your phone bill. You're going to pay your car insurance, whatever. So the first part of my money goes to my ATP, paying my bills. Then the second part of your money is you're going to say, okay, well, I just paid myself the first of the month. How much money am I going to need to get through until the first of next month when I pay myself again? You're going to figure out that amount and you're going to put that in your checking account. Your short-term storage, your glycogen, is the equivalent of your checking account. You're going to say, I need this much money for gas, for groceries, for whatever I'm going to do. And you'll put that away for that. Then you're going to take the rest of that money and you're going to put that in your long-term storage. That's the money you don't intend to use. You're putting it away for your next vacation, whatever. That's your long-term storage. That's your fats. Okay, so that was our caloric surplus story. Then the next story we'll tell is this. I've decided that Netflix and Oreos is probably not a good idea. So I'm in triathlon training now. And I'm living on chicken and lettuce. I need a carb in there with a very sugary dressing. And I'm taking in 2,000 calories a day. But with my triathlon training, I'm burning 6,000. So what am I going to do now? Well, those 2,000 calories will go straight to ATP. So I'll make ATP out of those 2,000. Where will I look next to fill in that deficit? I'll go next to my glycogen. I'll use my glycogen until I run out. Then and only then will I go to my fatty acids. That's my third place to go. I go to my long-term storage after my short-term storage. And we'll go through and tell that story, or we have. But remember, I can't break down my fatty acids until I deplete my glycogen. So quarter 1, we'll go and tell that story. Quarter 2 and 5, remember doing that story. No long-term storage until I deplete my short-term storage. Something I left off here. Be very cognizant of terminology. One of the issues that you have with boards is you don't know the topic of the questions. As we go through, we'll say, we have a test this week. Our test will be on, glycolysis and Krebs or whatever. You know the topic. The boards will give you a whole bunch of questions. Just throw them at you. You don't know if it's a fat, a carb, or a protein, an enzyme, whatever question. So be very clued in on the terms. GL anything is going to be a carb question. Lip anything, or ester, acyl, that's going to be a fat question. I should have put the term lipogenesis for making my fatty acids. I should have put the term lipolysis for breaking down my fatty acids. When I join a fatty acid to the backbone forming a triglyceride, I join it in an ester bond. If you see ester, you're going to think fat. If you see acyl, you're going to think fat. So anyway, that was my fat story. Then we said, okay, well, hang on here. Glucose isn't the only carb in the world. We're going to have some other carbohydrates. We're going to have things like fructose. We're just going to have to do a couple steps, feed into the glycolysis story. We're going to have lactose or galactose. Couple steps, feed into the glycogen story. So we'll have a whole bunch of on-ramps and off-ramps there too with monosaccharides, disaccharides. We'll have another process called the pentose phosphate pathway that gets sugars that are not 6-carbon sugars in there. So we'll have the highway built. At that point, it's just on-ramps and off-ramps. So that was our carb story. That was our fat story. When we're breaking down fats that somebody else made, say the fat that the pig or the cow made, we do the same process. I usually tell the story like we're breaking down our own fats, so you see how it fits into the metabolism. It's not really fitting into metabolism when you break down somebody else's, because it was fitting into their metabolism. You're just breaking it down because you ate that ribeye, the bacon, whatever you ate. Okay, the last part of the story is actually a really easy part of the story, and we're able to do it at the end kind of quickly because it's a real feed into what we've already done kind of story. We're going to break proteins down into amino acids. And remember the structure of an amino acid. So we break the protein down into amino acids. Whatever amino acid we have is determined by this side chain. And we've done that with everybody by the time you're watching this video. So the first process we're going to do is a process called transamination. What that does is it separates the amino group from the amino acid. That leaves me with a keto acid, also known as a carbon skeleton. And what that is an amino acid without its amino group. What that is a molecule that you will have seen already. So Dr. Krabbe will spend a lot of time with you on which one becomes which one and food sources and things like that. But when you do break them down, and a couple of common examples are aspartate, when I take the amino group off, will become oxaloacetate. Goes right into the Krebs cycle. Then you know what to do with it, how to get the energy out of it. When I take the amino group off of alanine, it'll become pyruvate. So if I tell you processed an alanine and got a pyruvate, you know what to do with that. That's what makes proteins kind of quick and easy to do. When we break down the amino acid through transamination and actually oxidative deamination, another process that we'll do, then it's a molecule that you've already seen, or actually we get the keto acid just through transamination. Oxidative deamination is part of how we're going to deal with the amino group. So we get the energy containing part of the molecule, we feed it in somewhere in the process we've done, good to go. We get our ATP out of it. A big part of our protein story, though, is about dealing with this amino group. What happens with the amino group is it likes to pick up another hydrogen. It likes to pick up another hydrogen and become ammonia. So if you don't need that nitrogen-containing molecule for something, we have to get rid of it. So we have to get rid of it, and we do that through a process called the urea cycle. So we do it through a process called the urea cycle that turns that ammonia into urea, puts the urea into the urine, and gets rid of it. So we get rid of it. It's gone. We can't leave that free ammonia floating around in the bloodstream because it's harmful. It causes harmful effects to your central nervous system, stuff like that you're going to do in a lot of other classes. So we do the urea cycle. And again, by the time we do that, you've got this process thing down. What molecule makes what molecule, how many ATP, stuff like that. So this is our way of getting extra nitrogen gone out of the system. So we'll also talk about some things here like storage. We have no protein in our body whose purpose is energy or fuel storage. That's a little bit different, and it's a little bit counterintuitive. We have carbs have a storage molecule, glycogen. Fats are a storage molecule. Our fatty acids are meant to store extra energy. Proteins have no storage. We've got to get rid of that extra nitrogen so it doesn't harm our tissues. So that's a little different in the sense that when we use your endogenous proteins as fuel, that's a secondary purpose to that. So we'll talk about that in terms of how to handle questions and everything. So quarter 2 and quarter 5, this was meant just as a review to pull pieces together. Quarter 1, what we're going to do with this is we're going to step our way through this. First process we'll do is glycolysis. We'll kind of lay our groundwork for how we're going to approach this. It'll take us, if we're in the classroom doing it, a couple days. I have a video on it that I think is about an hour, hour and a half. And then we go in the classroom and answer questions. Then we'll do the pyruvate dehydrogenase complex. So we're able to say, yesterday we went from here to here. Now we're going from here to here. Then we'll do the Krebs cycle. Started here to here to here. Now we're doing this. So we're able to say we're here, we're there, whatever, to kind of keep track of where we are, pull the pieces together kind of thing. So that's it for your big picture.